In this example, we're looking at the sequence an equals -1 to the n. Let's look at what the terms look like. Notice that because it's just this factor -1 to the power of n, that the terms are just going to alternate between -1 and +1. So each term just jumps back and forth between -1 and +1. And so on. Okay, so the question is, does this sequence converge? Well, there's clearly a pattern that's easy to guess what each term of the sequence would be. However, it does not appear that the values are getting closer and closer to any one particular value. In fact, as the sequence goes, the distance between consecutive terms doesn't appear to shrink. It just kind of stays the same, right? So it just jumps back and forth between -1 and +1, but does not appear to get any closer to one particular value as the sequence progresses. Right? There's no value that these terms are closing in on. So the sequence here we would say is divergent. Right? In fact, you can easily tell that the distance between consecutive terms is always 2. So that the terms never get close to each other. How about if I look at a sequence -1 to the n over n? Now this one's a little different. It's still alternating. So the terms of this sequence, for instance, would start with -1/2. Or I'm sorry, first term would be -1 over 1. So here let's just write -1 for the first term. Second term would be +1/2, -1/3, +1/4, -1/5, and so on. Okay, so they're still alternating in sign, but it appears that as the terms progress, they're getting closer and closer to 0. Right? So they start here at -1. And jump to +1/2, and then down to -1/3, and then up to +1/4, down to -1/5, and so on. So it's easy to kind of see that the values here are actually look like they're closing in on x equals 0. And one way we can establish this is to use a theorem that we said before. Since we know here that taking the limit as n goes to infinity of the absolute value of -1 to the n over n, which is really just the limit as n goes to infinity of 1 over n, we know this limit is equal to 0. Therefore, we had a theorem that says if the absolute value of the terms goes to 0, then this implies that the limit of the sequence without the absolute value also goes to 0. Okay, so there we're making use of that theorem that we wrote earlier. Here's a theorem that allows us to move limits inside of continuous functions. So what it says is that if I have the limit as n goes to infinity of an equal to L, and the function f is continuous at L, then the limit as n goes to infinity of f of an is equal to f of L. Okay, in other words, here I can take one way to think about it is I can take the limit inside the function. Like that. So let's try an example here. Suppose I have the limit as n goes to infinity of sine of pi over n. So we can think of this as the sine of the limit, since sine of course is a continuous function, sine of the limit as n goes to infinity of pi over n. Since pi over n goes to 0, this is just equal to sine of 0, which is 0. Here's an interesting example. It says, discuss the convergence of the sequence an equals n factorial over n to the n. Where n factorial, right, this is the symbol n factorial, is multiplying all the integers from 1 coming up to n. So n factorial is a type of operator that only applies to positive integers. Okay, so for instance, 3 factorial is 1 times 2 times 3, or 8 factorial is 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8. Okay? So if I'm looking at the nth term here, which is n factorial over n to the power of n, we want to think about what happens here as n goes to infinity. So if I write it out here, we know n factorial, that's 1 times 2 times 3 times so on all the way out to n. N to the power of n is really just n times itself, n times. So it's n times n times n, and so on. N times. So notice there will be a factor of n in the denominator that can be matched up with a factor in the factorial above. So we can kind of group the terms like this. So like 1 over n times 2 over n times 3 over n, so on all the way out to n over n. And perhaps looking at it this way is nice, because what we see is that it's 1 over n times a bunch of values that are less than or equal to 1, and we know they're less than or equal to 1 because, right, n is the biggest value here. 2 over n has to be smaller than 1, 3 over n has to be smaller than 1, n over n is equal to 1, but all the values to the left of it are going to be less than or equal to 1. So since we know all of these values here are going to be less than or equal to 1, then 1 over n times something that's less than or equal to 1 will be less than or equal to 1 over n. Okay, so with that fact, what can we say about the limit as n goes to infinity of n factorial over n to the n? Well, according to this, we showed that n factorial over n to the n is less than or equal to 1 over n. So the limit as n goes to infinity of n factorial over n to the n must be less than or equal to the limit as n goes to infinity of 1 over n. And this limit is 0. And clearly, n factorial over n to the n must be a positive value. So clearly this limit has to be greater than or equal to 0 as well. So we showed that this limit is both less than or equal to 0 and greater than or equal to 0. Therefore, it must equal to 0. So it converges, and in this case it converges to 0. Let's look at one more example where we're looking at the limit of the sequence r to the n. And the question is, for which values of r is the sequence convergent? Take, for instance, the sequence 2 to the power of n, right? Would this be a convergent sequence? Well, I don't think it would, because here, if I take powers of n, 2, 4, 8, 16, right? The values are just going to get bigger and bigger. In fact, they're going to get very large very rapidly. So clearly, in this case, when r is a value that's greater than 1, this limit is going to go to infinity. What about if I had a value that was smaller than 1? Say I had 1/2. Well, this case would be 1/2, 1/4, 1/8, 1/16, and so on. Now it's the opposite, that these values are getting smaller and smaller and smaller and smaller. In fact, they're getting closer and closer to 0 as the sequence progresses. So this kind of shows that in general, if I have r less than 1, then the sequence is going to go to 0. And then I guess the only other possibility is what happens if r is equal to 1. Well, if I have just 1 to the n, it's always going to be 1. It's going to be the same value for each term. So this kind of demonstrates the three possibilities here, that r to the n, when I take the limit as n goes to infinity, could potentially come out to be one of three things. So if we saw here, like when r is less than 1, the limit's going to go to 0. If r is equal to 1, it's just going to be 1. Or like what we saw here, if r is greater than 1, the terms are just going to get bigger and bigger and bigger. They're going to grow unbounded, so it'll go to infinity. Okay. Well, one thing we didn't consider is the case when r is negative. So, in fact, we can kind of adjust these a little bit here to account for the case when r is negative. So, for instance, what would happen if I took the negative 1/2 to the n? Well, this would be the same sequence here. It would just be alternating. But I think kind of observing what happened in a previous example, as long as the terms go to 0 in absolute value, the sequence must go to 0. So here, regardless of if r is positive or negative, as long as it's less than 1 in absolute value, it'll go to 0. So one thing here I can do is just adjust this so that it'll go to 0 as long as the absolute value of r is less than 1. And similarly, what about if I have negative 2 to the positive, or sorry, negative 2 to the n? As n goes to infinity, the terms here, well, they're getting bigger in absolute value, but again, they're alternating in sign, right? But they're still getting bigger in absolute value, so even though they're not going in the positive direction here, some are negative, some are positive, they're getting farther apart as the sequence progresses. So in this case, it would also be divergent. It would go to infinity, or in this case, if r is less than -1, I might say the sequence just does not exist. It doesn't go to infinity because some of the terms are going to positive infinity, while other terms are going to negative infinity. Okay, so there's our different cases that could happen here.